Hello, welcome back to the subterranean bunker deep underneath the 9000 labs here, where I've got one of my very favorite projects on the bench to show you here. This is my atomic Nixie tube clock featuring a whole bunch of neopixels. Quite a few years ago, maybe almost 20 years ago, I bought some Nixie tubes on eBay, and I was always intending to make a clock. But they just sat in the basement for the longest time. And then a couple of years ago, as Maker Faire was approaching, I thought, oh, that would be a great project to build for Maker Faire. So I got on it, and I'm really, really pleased with how it has turned out here. It's a little Arduino project here. So I will turn around and show you the backside here. This is my prototype, of course. It's mounted on a piece of plywood. So I've got an Arduino Uno here with the breadboard, controlling everything. Everything is mounted to a piece of laser cut acrylic here. There's a circuit board with the Nixie tubes and the driver chips on it, and there's another circuit board piggybacking off the back, which is the power supply. You need 170 volts DC for Nixie tubes. And you see this cable over here. As I said, this is an atomic clock. So this cable goes over to a receiver module that is picking up the signal they transmit from Fort Collins, Colorado, where they transmit the official US time. It's a 60 kilohertz signal, and they transmit 1 data bit every second. And you can see this red LED blinking on and off here, indicating that incoming data. It's 1 second per pulse, and they vary the pulse width on there to indicate the data bits there. So let me go get that antenna module and show you what that looks like. You can get these from a couple different sources. And they're not too expensive. And reception normally is not good down here in the bunker, but it happens to be good today. What this module looks like is there's just a loop stick antenna, and there's a little circuit board here with a epoxy potted chip on it, and then there's a little can crystal there, 60 kilohertz crystal for the carrier frequency. And then I get 5 volts supplied over the cable here, and a single demodulated bit of data goes back to the receiver there. What they do is they transmit the carrier at 60 kilohertz, and it's either at full power or at a reduced power to indicate the on-off condition there. So it's a kind of amplitude modulation there. It's not quite on-off because it doesn't go all the way off, but they dip the power way down low. Now, what you may have noticed here is that this LED stopped blinking. It's now just a solid red. What happens is that the power supply, the Nixie 2 power supply, is a switcher, and actually switches at about 50 kilohertz, and that is way too close to 60 kilohertz on the antenna there. So whenever you bring the antenna close to that power supply, the signal just goes out here. It will come back in a few more seconds here. I've moved the antenna back away about 10 feet. And I can see the signal now starting to come in again. Now I realize you can't see these neopixels very well on the on camera right now. In a bit, I'm going to show you a much better view where you can really see the colors that show up. But you should be able to make out that I've got 2 different colors on the screen here. I'm sweeping around the neopixels. The sweep is 1 per second, and there's 60 neopixels in that ring there. So I'm sampling that incoming signal 60 times a second. And whoop, I'm getting a bunch of noise right now. There we go. So you should see that there's a section of orange up here, and then a section of purple, and that corresponds to whether that incoming signal is high or low. So if you'd like now, I want to rearrange the camera and show you what those neopixels look like. I'm going to reflect the ring of neopixels in some dark acrylic, and then the colors will show up much better on video there. So let's switch over to that, and then we'll come back here and talk some more about how it's made. Okay, well now you can see the neopixels reflected nicely in this dark acrylic here. The Nixies are a little bit dim in this picture, but you can still make them out. In fact, the brightness of these neopixels really is a problem, not just trying to get it on camera, but even in real life. They're too bright. If you have this thing in a bedroom at night, you're not going to get to sleep. So I'm going to need to dim those down somehow in the next version. So as you can see now, it's got a good sync there, and the data bits are going around the circle there clockwise. You can see the red segment, which is the hour hand, and you can see the yellow segment, which is the minute hand down there. Across the top, there's a purple zone, which measures the drift that I'm seeing there. And everything else there is the circulating blue and green and orange data bits, the zeros and the ones and the markers there. So now what I'm going to do is press the reset button on the Arduino here, and it'll have to restart from nothing to figure out where it is. You see all the Nixies start blinking now. You can see I'm getting a real good incoming signal there, by which I mean there's no light purple within the orange and there's no orange within the light purple. I'm going to run that. Press the button and run that mode just a little bit longer. So you can read the data straight off there. That's a 0 and a 1 and a 0 and a marker bit and a 0 and a 0. And once it has seen 10 good data bits in a row like that, it switches the display mode over to this accumulated bits here. And you can see the new bits shifting in. So at this point right down here is where brand new data bits are coming in, and they're gonna circulate around like that. In fact, over there on the opposite corner, you can see the two greens right next to each other. That's the last marker bit of the previous minute and the first marker bit of the brand new minute. And you can see there's a green marker bit every 10 LEDs around the circle there. So when that pair of two adjacent greens gets all the way back around to where it started from, right about there, then I will have seen a complete 60-second data word, and I can extract the time value, and it will snap into view here. You can see while I'm syncing, I've got a blinking seconds counter on here, and I've got my rainbow backlights behind the Nixie tubes. Here it comes. It's coming. A couple more seconds, and bam. So everything lined up, and it was able to set the time, and I have to, this thing is in the mirror, so I have to bend down to see what time it is. It is 2:35 and 10 seconds, 2:30 in the afternoon, and that feels about right to me. Okay, well now I've got the camera pointed back right in the Neopixel, so they're swamped again. But there's a lot of information shown on there. The way the signal is actually transmitted is it's fairly straightforward, and it has to be because they started doing this in 1962 when receivers just couldn't be all that complicated here. So, you know, as I said, it's 1 bit per second with pulse width modulation to distinguish one of 3 different symbols that they transmit. They'll transmit a 0 symbol, which is on for 0.2 of a second and off for 0.8 of a second, or they'll transmit a 1, which is on for 0.5 and off for 0.5. I've got some extra noise indicated in there. And then there's a marker symbol, which is on for 0.8 of a second and off for 0.2 of a second. So what the Arduino is doing is simply sampling that incoming signal 60 times a second, saying, is it high or is it low? Is it high or is it low? And it shifts that data bit then into a big long shift register. And then it's constantly comparing the contents of the shift register to these 3 symbols here. Does the shift register look like that? Does the shift register look like that? Or does the shift register look like that? And eventually, once per second, it should say, yes, I see a 0, or I see a 1, or I see a marker. And that's how it demodulates that data. So once it's got those symbols there, it then shifts those into a secondary shift register, 0s and 1s and markers. And the markers are all about framing. So they put a marker every 10 seconds on the 9s, and there's an extra marker on the 0 second, the very first second of a minute. And so you pay attention to where you see those markers, and when they're all lined up in exactly the right place across all 60 seconds, then you say, aha, that's a valid frame of data, and then I can extract the data bits out of that and set the clock. So let's go to the WWVB Wikipedia page, and I can show you what those data bits actually correspond to. This is a really good article, and it tells you everything you need to know, more than you need to know. What I really needed to know to write the Arduino software is this table here. So you can see that there's a pink row indicates a marker bit. There's one at 0, and then there's one at 9 and 19 and 29 and 39 and so forth. And that's what you're paying attention to see when you've got your data word all framed up just right. And then once you see the right framing, then you can extract the data bits here. So there's 2 BCD digits that tell you the minute, and 2 BCD digits that tell you the hour of the day, and then the day of the year takes 3 digits. There's some extra information here about that I didn't pay a lot of attention to in this version. That seems to have to do with sub-second accuracy there. So I think when I build version 2 of this, I'm going to pay more attention to that and actually do something with it. There's 2 BCD digits for the year. There's a leap year indicator. There's a leap second indicator, and leap seconds are fun. They get inserted on an irregular basis as determined by some astronomer somewhere to compensate for I guess the change of the Earth's orbit. And what will happen is that it's decided well ahead of time that we're going to insert a leap second, and leap seconds go in as an extra second inserted in the very last minute of the month of June or the very last minute of the month of December. So a few months ahead of time, that leap second indicator would turn on, and then the clock knows that when I get to June or when I get to December, the very last minute or last hour, I've got to stick in 1 extra second, which means you would count from 0 up to 59, then count up to 60, and then go back down to 0. And then the last bit in the data frame there's 2 bits about daylight savings time. Is daylight savings time active? Is standard time active? Are you about to transition to daylight savings time, or are you about to transition back to standard time? And that's really all there is to do. You demodulate that signal, and when everything looks good, you can grab all those data bits and you can set the clock. There's more to it, and I won't go into great detail on this, but you don't get the signal all of the time. You only receive the signal when the weather cooperates. And so you can go minutes, hours, weeks, months without getting very good signal. It has a lot to do with weather conditions and the time of year. Okay, if you have an atomic wall clock, a battery operated clock that you hang on the wall, it's got a regular clock module in it, and it's got the extra receiver in it. The receiver won't be turned on all the time. In order to save battery, it's only going to turn the receiver module on typically late at night when the signal propagation is the best. And it's going to turn the receiver on, decode the signal, for a few minutes to get a lock and decode the signal, then set the local clock and then turn the receiver off, and then wait for another 24 hours and turn it back on again. So the easy thing to do for the Arduino would have been to get a real-time clock module and basically do that. Receive the signal, set the real-time clock, and then call it done. But what fun is that? I wanted to turn the Arduino into a real-time clock. And there's a challenge there. One is that the crystal on the board, the 16 megahertz crystal that runs the Arduino, is not super accurate. It's very likely not a quartz crystal at all. It's going to be a cheaper ceramic resonator, which doesn't have the same accuracy. And in any case, it's going to have drift with temperature or with age. And so your 16 megahertz that you're starting with is not really 16 megahertz. And even if it starts off as 16 megahertz, it won't stay 16 megahertz. So what the Arduino has to do, in addition to merely decoding that signal, is it has to monitor its own free-running clock and make some adjustments on that. If I start to realize I'm drifting a little too fast, I need to slow down. If I'm drifting a little too slow, I need to speed up. And so it's actually always computing how much it's drifting, and then it's recomputing the divisor factor that you need to get the 60 hertz. The way that you get the 60 hertz sampling frequency is you use the counter timer compare circuit on the Arduino. There are 3 of them. 2 of them are only 8 bits wide, and so that's not quite enough, but one of them is 16 bits wide, which works out well. And that's fed by the main clock, the 16 megahertz. And the way that works is you'll set a compare value in a register, in the 16-bit register. The counter is going to count up from 0 until it matches that register. When it does, that will trigger an interrupt in your software, and then reload the counter with 0 and continue counting up. And so it's a hardware process, and you get an interrupt happening at a regular interval. Now, if you figure out what the divisor is to go from 16 megahertz down to 60 hertz, it's too big to fit in 16 bits. But there's an extra feature in there. You can use there's a prescaler in there which will divide down that 16 megahertz to a lower value. So I divide by 8 to get 2 megahertz. And then the divisor you need to get from 2 megahertz down to 60 hertz is 33,333 and a third. And that 1/3 is kind of interesting. But what you do is you load that 33,333 in your compare register. And then in hardware, it's simply going to count up till you get there, reset, raise an interrupt, or not reset, but reset the counter, and then raise an interrupt, and that turns into a 60 hertz interrupt, and that's what samples the incoming data bits there. Now there's a lot more to it because one, there was that 1/3 fraction, so how do you deal with a fractional divisor? If you didn't account for the fraction, you just rounded it off at 33,333, you're going to be off by about 1 part in 100,000, which doesn't sound too bad, but in a clock that you would like to keep accurate time for days, weeks, ideally months before drifting noticeably, 1 part in 100,000 is not that much. So you have to, as I said, in addition to just ticking off the 60 hertz frequency and doing the sampling, you got to track, am I drifting a little bit with the incoming signal there, and then adjust that 333,000 or 33,000 value up or down a little bit to compensate for that. So it turned into being really a very interesting kind of software project here. It was more of a software project than a hardware project. But let's talk about the hardware here. The first step was the high voltage power supply. You can just buy, there's a few of these are available from different sources, you can just buy them, but I wanted to do my own circuit board layout. I'm not much of a power supply designer, especially high voltage, but I found a good website that had a good design, had the circuit schematic there, it had the bill of materials, you know, the specific parts to buy, the specific transistor to use, and the specific inductor, and that's very useful. And although it had a circuit board layout, I decided I wanted to do my own layout in KiCad. And fortunately, on the website, it had a lot of the things to watch out for when you're laying out the circuit. Things like, you know, certain loops in the schematic there, they should be very close together, and certain traces on the board should be nice and wide and short so they don't have too much inductance, and a lot of tips like that. So I used KiCad and laid out the board and sent off to, as you can tell, OSH Park, because it's a nice purple circuit board. And when the board came back, I soldered it all up and it worked first time, so that was really, really satisfying. So now the power supply was out of the way, so now the next step is the main driver board here. And you can see there's not too much on it. There's 6 chips on there to do the driving. It turns out to be straightforward to drive Nixie tubes. I didn't know what it was going to take, and actually Dave Jones had a video on how to do it, and so I just copied that method exactly. So what these chips are just a variant of the popular 595 shift register that you're always using with Arduinos, with a couple of features that help out. So the chip I'm using is the TPIC 6B595, and that is the same chip I used on the flip-dot display for the driver there. And what that is an 8-bit shift register that has open drain transistors on the output with an extra little Zener diode across there, and that is exactly the thing you need. So the way that you drive a Nixie tube is you put the 170 volts through a current limiting resistor into the anode there, and then when you want to light up a segment, there's a cathode lead for each of the 10 segments inside the tube. You just ground the cathode corresponding to the one you want to light up. So you connect that to the output of the shift register there. It's a open drain transistor. When you turn that transistor on, it's going to ground that output and the Nixie tube lights up. Then when you turn the transistor off, ordinarily without this extra Zener diode here, what would happen is this pin on the chip would then float up to the 170 volts, and that might destroy the chip there. So what saves you is they have this very convenient 50 volt Zener diode across the output here, which limits the voltage you'll ever see on that pin up to 50 volts, so it doesn't damage the chip. And then in the off condition, then you'd have 170 volts on the anode side, you would have 50 volts on the cathode side, but that only leaves 120 volts across the tube, and that's not enough to light up a Nixie tube, so the tube goes out. So really you don't even need any external components. You just attach the cathodes of the Nixies straight to the outputs of the shift register there. Couldn't be easier to do. And so that's what you see here on this board. I've got those 6 chips there and the 6 Nixies there. You might think, because it looks like it's a 1-to-1 mapping, but it's not quite, because if you do the math here, you've got 10 segments on every Nixie tube and 6 tubes, so that's 60 segments you could potentially want to light up. and there's only 8 bits on each chip. 6 chips, that only gives you 48 bits. And what the reason it works out is you don't actually need every combination of digits for a clock here. For on the units digit of seconds here and minutes and hours, you want to light up 0 through 9, so you need all 10 segments there. But for the tens digit here on seconds, you only ever need to show, you think, 00 up to 59, so you only need 6. Actually, because of leap seconds, sometimes you want to show a 6 on here, 60. So you do need 7 segments over here. You only need 6 segments over here. So the way this is wired up is this guy needs all 10, so I use all 8 from the chip here, and I steal 2 from the neighboring chip. Then this one needs 7, so I take the, what do? I take the 6 that are left over here, and I steal 1 more from the next chip, and so on down the line. And what really saves you is that the leading digit only ever needs to show a 0 or a 1 or a 2, so you only need 3 elements over there. So with 48 outputs, I think you end up using 46. I think that sounds right. Maybe it's 47. And so it just works out with the 6 chips there. So on the board, you can see you see the Nixies and the shift registers there. You see some neopixels here. You can see them lit up on the face of the clock there for the colons. What you can't see on this board is that underneath each of the tubes there is another neopixel to provide the backlight. Because what good is a Nixie tube without a neopixel backlight here? So there they are. It just barely fits inside the footprint there to have the neopixel and the little decoupling capacitor you need for it. So that's a chain of 10 neopixels there. There's a connector on the back here where you connect in the ring to get 60 more neopixels. And also there is a little 5-volt regulator on the back here. So the 12 volts DC goes into the power supply board, which produces the high voltage for the Nixies. And the high voltage goes through this connector here. And also the 12 volts goes down onto the board and then goes through this 5-volt regulator to supply the Arduino and the rest of the stuff there. And so there's really not all that much to the board. As I said, this was primarily a software project, it's one of the more complicated sketches that I've done. It's got a little bit of inline assembly in there to make a really fast shift register. Probably could have done without that, but it was just fun to experiment with that. And so I'm offering this video up as kind of a teaser. I'd like to do version 2 of this board. There's some changes that I'd like to make. In addition to toning down the neopixels on the front here, I would like to use a different driver chip that's denser. So instead of 6 chips with 8 bits, it would be just 2 chips that have 32 outputs each. And that would give me 64 total, which would be more than enough to drive all the segments of all the Nixie tubes all the time. And you'll notice on the display, I'm only showing the time of day, even though I can actually decode the date as well. So I'd like to add an additional display on here so I can show the month and day, and maybe display some extra information. That additional display would be an OLED panel. And if you're going to use one of those OLEDs with an Arduino project, you're going to need some storage space for all the graphics and the character symbols that you use on there. And so there would be an SD card on the board as well to hold all that information. Now, once I've got an SD card on the board, I might as well start logging some information, like how is the clock drifting over time. And one additional thing I'd like to put on there is a temperature sensor somewhere to sense the ambient temperature, because I'm pretty sure that most of the drift that I see in the Arduino's time base is temperature sensitive. So I'd like to put a temperature sensor on there somewhere and simply log the temperature and see how that causes me to have to change that divider value for the counter timer to get my 60 hertz time base. So there's a lot of things to talk about. I kind of glossed over some of the details on the software about how do you do that drift and how do you detect the drift and how do you compensate for it. A lot of interesting stuff to talk about there. I think it's going to be a challenge to get it all powered by an Arduino Uno. Once I add on an SD display, I think there's enough program storage space, but I think I'm going to be awfully tight on RAM. I might not have enough RAM, so that might mean digging into the libraries for the OLED display board and see if I can sacrifice something to save a little bit of RAM there. But that's the fun of doing these projects. Is, you know, I like to get the microcontroller, get a nice simple 8-bit microcontroller, and push it. You try to use every feature and push it as hard as I can, get the most out of it, rather than just get a fancier board, a 32-bit board or something like that. So as I said, this video is kind of a teaser. If you would like to see more about the Nixie tube clock, you know, as I design it, leave a thumbs up, you know, leave a comment, ask a question, and if I get some positive response, then I will start making some more videos about that project. So I hope you enjoyed seeing this here. I hope it was educational here. And my camera just shut off here, so I think this video is done. Bye-bye.